In our previous video, we talked about average rate of change, and it was across an interval. And in today's lesson, we're actually going to be focusing instead on this instantaneous rate of change, or IROC. IROC looks at the rate of change across a very small interval, okay? Basically across an instant, hence the name instantaneous rate of change. Essentially, this is like a secant line, just with a very small interval instead. And then, of course, the smaller the interval we get, the more quote-unquote instantaneous the rate of change is going to be. Let's look at an example of what this is looking like. A golf ball is hit and follows the curve modeled by the function h of t is negative 4.9 t squared plus 25t, where h is the height in meters and t is the time in seconds. Estimate the instantaneous rate of change. We're going to do this a whole bunch of different times to just see how close to instantaneous we can get, okay? What's missing from the question here is the point of reference, so we're going to say at 3 seconds. Estimate the instantaneous rate of change at 3 seconds. So the first interval we're going to try is between 3 and 4. Okay, so what I'm going to do here is I'm going to substitute in, I'll do my 4 first. So I have negative 4.9 times 4 squared plus 25 times 4, and that is 21.6. Then I have my h of 3 is going to be negative 4.9 times 3 squared plus 25 times 3, which is 30.9. So in this case, my delta H will be 21.6. Take away 30.9. I don't know why I drew that so high up. There we go. Which is about 9.3. Negative. My delta t here, we went from 4 to 3, so I'm going to do 4 minus 3, which is 1 second. And then our average rate of change, of course, we're going to do delta h over delta t. So that's going to be negative 9.3 divided by 1, or negative 9.3. That's when we use the interval of 1 second. Can we get even more precise if we use a smaller interval? Like, let's say, what if we went from 3 seconds to 3.5 seconds? What if we did that instead? We've already calculated h of 3. Sorry, that should be a square. So I'm going to do h of 3.5. 4.9 times 3.5 squared plus 25 times 3.5. And this will be a 27.475. We already know h of 3 is 30.9. So I can calculate my delta h. We'll go 27.475, take away 30.9, which is negative 3.425. Our new delta t here, remember we went from 3.5 to 3, which is just a ½ second difference. So our average rate of change here, we're going to go negative 3.425 divided by a half, and this gets us to negative 6.85. This is closer to being precise. We're using a smaller interval, but I actually want to get even smaller. So I'm going to do this a couple more times. What if we went on the interval between 3 and just 3.1? Okay, substitute 3.1 in. Negative 4.9 times 3.1 squared plus 25 times 3.1, and this is going to be 30.411. We have our h of 3 from before. Our delta h will be 30.411. Take away 30.9, which is negative 0.489. This time we're working on an interval of just 0.1. And if we go negative 0.489 divided by 0.1, that's negative 4.89. Notice how the rate of change, the average rate of change is decreasing, but we are getting more precise. We're working on a smaller interval. Let's try a smaller one. What about this time between 3 and 3.01? Okay, calculate h of 3.01 is negative 4.9 times 3.01 squared plus 25 times 3.01. Put that into a calculator, you're going to get 30.85551. So my delta H will be 30.85551. Take away 30.9, which is negative 0.04449. Our delta T this time, it was on an interval of 0.01. So the AROC, negative 0.04449 divided by 0.01 is negative 4.449. Aha! We're getting closer to instantaneous, okay? Our results are getting a little bit more precise. Last one that we'll see. Let's check against the interval between 3 and 3.001. H of 3.001 is negative 4.9. 3.001 squared plus 25, 3.001 is going to be equal to 30.8955951. And I'm writing out all the decimal places intentionally because I want to be precise. Delta H is going to be 30.8955951. Take away 30.9, which is negative 0.0044049. Whew! This time our delta T is 0.001. And then, of course, our new fraction, negative 0.0044049 over 0.001, negative 4.409. Notice how much closer we are getting. More like it's looking like the first number is definitely going to be a negative 4. The second number is definitely going to be a 0.4. And then we're working our way there. Okay? In math words, essentially what's happening. Oh, and this got cut off. On a curve, as point B approaches point A, the slope of the secant line between them is approaching the slope of the tangent line. Okay, so if we have a graph, and I've got some kind of curve, point A, point B, every time this point B, the second point that I'm using, gets closer and closer and closer, we have here, originally we have a secant line, but the closer it gets, the tighter it's going to be to that A, it is going to approach the slope of the tangent line. And the tangent line is that instantaneous rate of change. Okay? A tangent line, if we look at a graph here, we'll use this graph, okay? So here we're being given an example where the path of a diver off of a diving board is modeled by the graph below. We need to figure out what the instantaneous rate of change is at 1 second, which means we're looking for the tangent line. More specifically, the slope. And what the tangent line is going to look like, I'm going to zoom in. This is the point right here we're interested in. You want to take your ruler and you want to draw a line that only hits the graph once at approximately that point. sort of reflecting off, something like that. Okay, where it's kissing, the line is just kissing at that point that you're interested in. Okay? So an IROC on a graph, okay, what we're being asked to find here is we're being asked to find the instantaneous rate of change using the tangent line. What's going to happen here is we are going to use the instantaneous rate of change. Okay, we're going to use this tangent line that we have sketched to help us try and figure out what the instantaneous rate of change is at this 1 second. Okay, so I've drawn the instantaneous rate of change, or the tangent line, as best as I think that I can. I'm just going to extend it here in both directions, just a touch. There we go. Because we're being asked to find, oh, zoom out, come on. Okay, we're being asked to find the instantaneous rate of change, which means that we're being asked to find the slope of this tangent line. At 1 second. Okay, so that's why I extended it to help make it easier to find the slope of the line. We're going to use our points here, we're going to try to find 2 nice points to help us figure out what the slope of this line is. I know that I can use this point, that's at 1,6. Looks to me like maybe right here we have another sort of good point. That looks to be located at 1.5 and 5.5. So we can find the IROC that way. Our IROC, of course, is our delta y over delta x. So in this case, I am going to have 5.5 take away 6 divided by 1.5 take away 1. So that'll be negative 0.5 divided by 0.5, which is about negative 1. Okay? We'll see how close we actually are. So when you're asked to find the instantaneous rate of change on a graph, you need to be sketching what that tangent line looks like and then finding the slope of the tangent line. Now, if you're given an equation, what you need to do is what we had done up here, except you're going to jump right to this bottom step where you're using 2 points that are so close together and you're finding the slope between them. Okay, the goal of this chart was just to show you that the closer the 2 points get, the more precise the slope is going to be at the end of the day. Okay, so here we are being given the equation of the diver's height is this. Okay, negative t cubed plus 2t plus 5, where h is the height in feet and t is the time elapsed in seconds. Let's determine the instantaneous rate of change at 1 second and then compare to our estimation from the graph. Okay. The interval is at 1 second, we're interested in 1 second. So the interval that I'm going to use is between 1 and 1.001. That's what I'm going to be checking against. Okay. You could add more zeros in there if you wanted. You know what? Let's do it. Let's do 3 zeros and see how precise we can be. Okay, we need to find what our function is at these 2 points. First, I'm going to check h of 1.0001, so that'll be negative 1.0001 cubed plus 2 times 1.0001 plus 5. Do this all on your calculator, and I'm going to get 5.9998997, something super precise. Let's find h of 1 now. That'll be easier. Negative 1 cubed plus 2 times 1 plus 5. This will be negative 1 plus 2 plus 5 is 6. And so we can find our instantaneous rate of change by going 5.999 9, 9, 9, 8, 9, 7. Nope, I'm missing a 9. Minus 6 divided by 1.0001 minus 1. Okay, and this will be, type into my calculator, 5.99989997 minus 6. I have negative 0.1231 and a 3 divided by 0.0001. My answer is negative 1.003. That is pretty good, given we approximated that it would be 1 or negative 1. That's pretty good, my friends. We drew a decent instantaneous rate of change, a decent tangent line on our graph to begin with. Okay, so this is the more accurate instantaneous rate of change because we were able to use the formula versus just sketching it on a graph. But the goal here is that you understand what a tangent line looks like on a graph, just like this, and then also how to estimate it using the graph and using the equation. Good work, everybody.